Good evening, Doctor. This is Nachamba de Mariam from Group ML SWML 53, and I'm going to present to you the Unexplainable Dual-Module Ensemble architecture for microfinance, and it's credit scoring under severe class imbalance and institutional domain shift. Basically, this is the content of presentation. We have these contents, introduction, and everything, as you can see. To go straight into the background and introduction, Uganda's microfinance sector has over 2,000 institutions in savings and credit corporation in Uganda, and it's managing 3 trillion Ugandan shillings annually outside formal credit bureaus. It registers a portfolio at risk of 15 to 25%, which is too high compared to the 5% of the global benchmark, and that makes it that over up to 25% lent money may never return. So we looked at the credit bureau gap, and it's a tier 4 institution. Since it's a tier 4 institution, it cannot check cross-institutional borrowing, and there is a silent double dipping, which is undetectable. One of the reasons as well is also the appraisal bias. This happens because loan decisions are based on relationships. Someone can acquire a loan because they are known, but not because of the capacity to repay the loan. We looked at 2 modules. The first module is the gatekeeper, which works on the pre-disbursement of the loan, and it's a binary default prediction, and it predicts money before it is given to someone. And we also had second module, which is the monitor, and this one works on the post-disbursement, and it works with 3 class early warnings. There is the stable, elevated, and critical for the loans that are active. We had to use the XG boosts. The XG boost is a gradient boosted trees, which basically optimizes inductive bias for heterogenic tabular credit data with missingness. As I will explain later on, we had to use SHARP, and which is a model for agnostic attribution satisfying the Uganda Data Protection Act of 2019. We had the area under precision recall curve. We also had 4.3 to 1 class imbalance ratio, and then we have the group shuffle split. The group shuffle split, it worked with the disjoint test and train and test splits, and it evaluated entirely unseen cooperatives. So to dive straight into the related works, we have the AI in banking. These are the sources that we had, and these are the modules that we used. In AI in banking, we used the logistic regression, which was a linear model, and these are the results. It registered the area under curve of 0.7 to 0.78 on bureau data, and the limitation we saw was that it's a linear module and it fails nonlinear circle interactions. We have I'll not explain everything, but I'll pick out some few. We had the credit risk analysis using the light GBM. We used the light GBM and XG boost, and this is the area under curve. It was 0.87 on the peer-to-peer data, and then it tuned on P2P, and there was no informal sector features. And it means that no collateral paradox or season patterns were modeled. These were the limitations, the architectural and the contextual limitations. We also had the credit risk assessment model. It used the random forest and the SVM, and this accuracy was 79% on consumer credit. The architectural limitation was that there was no SHARP and the black box for regulators, and the contextual limitation was that the consumer credit was that there was no microfinance or informal sector data. I'll go straight because of time. I'll explain the problem statements. The problem statement, we looked at three basic problem statements, and we had that the first was the appraisal bias, where the loan officers approve based on relationships, based on what people, on how they're related to people, or maybe someone is their friend or their good customer in an institution, but they just give them not because of how the capacity they can of how they can repay the loan, but because of how they know them. And that's a problem. It causes a loss. And then we also had the identity and trust gap, whereby people use used credentials that are not theirs. They acquire loans basing on credentials that belong to other people. Like in Uganda, someone can acquire a loan that's for someone and use an identity card that's for someone else, or they can tell the other person, borrow for me a loan. That's identity and a trust gap. Then there is the blind spot. The blind spot is where there is no early warning for deteriorating loans, and by the time a loan is formally non-performing, collateral may have gone and recovery may be nearly impossible. The computational problem, we had a 3.1 ratio, 3.1 to 1 ratio class imbalance, where 24.35% base was a default rate, and they also had an institutional leakage, a data quality crisis, a minority class collapse, and these are the computational problems we registered. These are the research questions that we had and the objectives. The objectives was to conduct a 24-question EDA, as I'll explain next. Then the research questions was the borrower, loan structure, contextual features, and the rest. Then the second objective was to design, train, and compare 5 ML architectures. These basic 5 that we used. We deployed a Flask REST API. We had the question that what early repayment trajectory features reliably distinguish stable, elevated, critical, and elevated and critical loan risks. We established a 3-phase deployment framework, and it included the shallow, assisted, and policy, which were measurable circle level performance in the gating criteria. Then I'll go straight to these were contributions we made and the outputs. So here we have these two modules. We have the application gatekeeper, which acts as the pre-disbursement. This application gatekeeper inputs borrower demographics, then the loan requests, and then it looks at models of it basically is the XGBoost model, and it had the preprocessor, robust scaler, one hot encoder, and the outputs with the default probability. I'll explain about this. Okay, this gatekeeper, it works on the first on the details someone has given in at first hand. Like okay, like this pre-disbursement module, it detects after someone entering the details. It helps to predict whether this person can actually pay the loan, or the person isn't able to pay the loan of that given amount he has applied for. And then the second module, which is the running loan monitor, it works on the post disbursement of the loan, and it provides a 3-class risk classification of the stable, elevated, or critical on that active loan the person has acquired, and it uses a repayment trajectory features which are unavailable at origination. So basically we saw that the second module architecture is fully specified. Training and evaluation differs to a companion publication. I'll go to the XGBoost, which is the production model. It is the basic model that we used. XGBoost works with this function. I'll explain about this function. This works with decision trees, and it has a given number of trees, and it works on these decision trees sequentially, and it corrects each tree with residual errors from the previous ensemble. And this function, the objective function, balances the prediction quality and the model complexity. In this diagram, you can see that when we have tree 1, this is the first. Okay, it's the base. So it predicts residuals from base, and then the second tree it targets errors from the first tree. Then the third tree fixes the second tree's mistakes, and then up to the 600 tree. The 600 tree has the 600 tiny corrections in total. It also uses a sigmoid. This sigmoid function, you've seen it. I'll go to the modules because brain is coming. I'll go to the modules. We have the logistic regression. I will explain briefly about each of them. The logistic regression computes a linear combination of input features which are mapped through the sigmoid function, this function here, and its weight vector and the bias feature work together with the vector x and the probability default and the predicted default probability is computed after using this function. This works with mainly linear features. So we now went to the random forest. The random forest is the one that uses decision trees on bootstrap samples, and it averages their probability outputs while denoting this function. Then we have the cat boost. The cat boost is like, okay, it orders, but it uses the categorical variables in the circle, such as the employment status, the business type, the district. So this one helps in categorizing and ordering the features, which leads to the curse of the dimensionality on the model. Then we had the light GBM. The light GBM, this gradient boosting machine works with leafwise. Like, for instance, you see that it's a leafwise growth for edge device efficiency. So this one goes to the best first, like how you see the feature which can give you high results. So it goes for that best first, and it focuses on computing efforts on the leaf with the highest loss reduction, and then it enables deeper and more accurate trees with low memory usage. Then we had the EBM. This is the glass box. The glass box works with regulatory compliance. We use this function. Then we had the tabnet. The tabnet, which is the sequential sparse attention. For this tabnet, basically, it uses a sparse, as you can see here, a sparse mask function. So this sparse mask function selects and processes feature subsets at each of the S decision steps. And then at each step, there is an attention that is masked, and it's generated from the prior steps features using a shared fully connected layer with a sparse mask. It's registered as 0.78, and then we went to the tab transformer. The tab transformer It maps categories to dense embeddings, and it contextually updates via attention layers. Here, what it does that it maps each categorical layer to dense embeddings via the learned end-to-end layers. So these embeddings are passed through the multi-head self-attention layers and thereby presenting by attending to all the other categorical variables in the same record. That's how much I can explain. This is the function we use. Then we have the decision tree. The decision tree, okay, for it's like a final, like, okay, this one uses final architectural component, which is the distal student, and it's designed for the maximum speed and zero dependence deployment. Thereby, it trains not on the raw binary labels, but on the soft targets. As you can see, the function, it has the distill. Yeah. So I'll go to the data set EDA. A data set comprised of 19,955 training eligible records, and it records from 46 circles across 15 districts. These were the variables. The target was that we use the default flag, which flags one, and then the one for the default portfolio at risk, it will flag 0. Then the class ratio was 25.53, and it registered a 3.1 to 1 ratio, and the imbalance was it performed on 15,060 records out of the fourth, and it left out the 4,895 which were defaulted. These were the results from the EDA. This is the class imbalance. Class imbalance, this one works with the first loaner, second loaner, third, fourth, like that. So we see the first loaner, how they are able to pay the second loaner like that. Then we looked at the borrower loyalty effect, people who are acquiring loans for the first time, and people who are acquiring loans after many times. Then the school fees seasonal effect, when students go back to school, and that time when they are back from school, how are loans repaid. And you can see that I will sample that in May, when students are back from holidays, it's low because parents are not paying school fees. But when it's in January, you can see that there is a high default rate because students are going to school. We looked at the output results. These are the results from all the models that we used. The logistic regression had 0.4, and this was 0.68. But I'll go straight into the main. Why we called this one, we called it the main. This one registered as 0. According to this, because we are following this, it registered 0.06 on the F2, and then it registered as 0.4006 on the F1. And XGBoost was actually, it's a bit average. It's in the average bits. That's why we had to choose it. It performed better than the rest. And this was the tester board. And to go to the compression. This was the analysis we got. Then the explainable AI results. These are results we got from the explainable AI, the SHARP, what SHARP predicted, and we looked at those loans that require, those loans that are, why we have high risk loans rejected and why we have low risk loans accepted. Then we have the model selection. Here, the reason why we had to use the XG boost is basically it has a best cross circle stability. When we tested with F2, it was 0.76 and up to 0.61 across the 6 circle group split reshuffles. And it confirmed a clean causal feature, which led us to the 7-step leakage audit. It followed a deployment pipeline system architecture where we had to get, then predict and get, post and get, and we had to perform a deployment plan which showed the shadow mode, and here it runs parallel with manual process. It logged predictions and there were no decisions altered. Then the second phase had assisted decisioning. It had high-risk applicants routed to senior officers with sharp list. And then phase 3, it had policy integration where we automated decisions after the F2, which was greater than or equal to 0.70, and it sustained only 60 days. When we go to the model compression, so model compression, what I would say, given the fact that we had a tier 4 bureau gap, model compression primarily used a primary objective, and it is a primary objective and the teacher module. So the primary objective was that it's going to deploy a highly robust credit intelligence engine across a diverse circle and micro environments and process loan applications with the lowest latency possible, while the teacher model, which is the heavyweight XG boost model comprising over 600 trees, at the depth demonstrating a strong pattern recognition, and this size presents demonstration friction for resource-constrained circle infrastructures. And this lacks the ultra-fast execution required for real-time loan origination. And we had to have these steps. We had the first step, which was to extract and reveal hidden relationships between classes by smoothing the teacher's confidence. Then the second was to transform. Using this function, it strips the sigmoid compression to retrieve the teacher's raw decision conviction. And then the third was to distill, and this was to create the expert advice and the targets that the student model is trained to mimic. Then you go to the distillation pipeline. This pipeline followed a structured 5-stage pipeline to ensure that the student captured the risk profiles of the Ugandan lending data and was rigorously engineered to prevent the data leakage and ensure that an apples-to-apples evaluation across all modules. The first was data loading and identical preprocessing, and this one basically was to eliminate data leakage and extract circle-aware group shuffle split, which is generated in the main training phase, and it was reused. Then the second was establishing the teacher's baseline in the context of the knowledge distillation. The baseline acts as the teacher's report card. And then the third was to generate soft labels. The soft labels, it trained the data set. The training data set was passed through the fitted teacher to extract probability distribution rather than the binary 0 to 1 inputs. Then we had the loss blending. The loss blending here, using this function, the student was trained on the weight targets and blended Y as the calculation goes here. Then the student training section, it had 3 distinct student architectures which were trained, and it evaluated against their hard truth baseline and against their baseline. So they were then compared against each other, from which the best student was selected. Among the models include a linear logistic regression, which is the single decision tree, and a small gradient boosting machine. They were trained to predict these two targets instead of the row broken targets. And the results, I'll go to the next slide. The results were as follows. Here are the results. Because of rain, I want to explain faster. This is the performance breakthrough. The students surpasses the teacher, and then there's a single decision tree student that achieved significant performance gains over the 600 free XG boost feature. We deployed this, and I'll open my browser. After filling in credentials here, I'll come back. The loan officer enters the borrower details in a web form, and then it generates for them the risk at which someone is going to pay or not. Then we had this is the product interest rates at night. Then the limitations we had evaluation scope. Module 2 could not handle the evaluation scope because of the limited results. Then we had the geographical institution focus, and then the class imbalance of 3.1 ratio. This was also the temporal and policy sensitivity. We also had the infrastructure prerequisites, whereby some systems assume digital record keeping while others use manual level environment. This is the conclusion that this explainable AI architecture is the first circle-distributed, linked, audited ML credits framework for Uganda's Tier 4, and it addresses a critical gap in East African fintech. The references are as follows, and we acknowledge our supervisors, Dr. Galiwango Marvin and Dr. Efrens Eunice Namujeni. Thank you so much for being good supervisors and very, very kind to us. We also acknowledge Makerere University, the SAFO partners, and the community of UMRA. Have a good time. I remain Natamba de Mariam.